Hi folks, we're going to take a look at the solution to number 14 on page 419. So they tell us that A and B are unit vectors. So remember that means that they have magnitude 1. And they give us that the magnitude of A plus B is equal to square root of 3. And then they want us to determine this expression. Okay, so first of all, I'm going to use the distributive property of the dot product to allow me to write this expression into a bunch of much simpler ones. Okay, so let's apply the distributive property here. So here we have 2 A dot B. Here we've got plus 6 A dot A. Okay, here we've got negative 5 B dot B. And then finally we have negative 15 B dot A. All right, so now what I've done is I've turned this into a bunch of much simpler operations. Why are they simpler? Well, because we know that A dotted with itself is just going to be the magnitude of A squared, and B dotted with itself is going to be the magnitude of B squared. The magnitude of, magnitude of B squared. And that these two terms are actually like terms because of the commutativity of dot product. A dot B and B dot A are the same. So I can simplify even further. So here we've got 6 times the magnitude of A squared. Here we've got minus 5 times the magnitude of B squared. And then here we've got 2 minus 15, so minus 13 A dot B. All right. These are unit vectors. So these just have magnitude 1. Squared is still 1. So 6 minus 5. So we're left with here just 1 minus 13A dot B. Okay, so we've taken this whole expression, and after expanding and simplifying, we've essentially reduced it to just determining A dot B. And this is where we can take 2 approaches. So I'll show you both because, sometimes you might not think of one, but there happens to be an alternative here. Okay, so one of them is a geometric alternative and the other one is an algebraic alternative. And I would say they're about one as easy as the other. Okay, so let's do option 1 here, and let's take the geometric alternative. So the geometric alternative tells us that A dot B is the magnitude of A dot the magnitude of B times cosine of the angle between them. So these are both unit vectors. Okay, so 13 cos theta. So it's just a matter of determining the angle between A and B, and that's where we can bring in the sum. Okay, so if we draw ourselves a little diagram, we have here that A plus B, okay, both magnitude of 1, and then their sum is just equal to square root of 3. Okay, and so what I can do is find this angle here, theta, which of course is not going to be the angle between the vectors, okay? But if I put the vectors tail to tail, we see that the angle between them is just going to be 180 minus this. So if I find theta, okay, that's just cos inverse of, so this is the opposite side, so this is root 3 squared is 3 minus 1 squared minus 1 squared, all over negative 2 times the other two sides, 1 and 1. Okay, and so here we have that it's just cos inverse of 1 over negative 2, so negative 1/2. Okay, now this is one we've seen very often, so it'd be good if you just kind of knew that, but just in case, okay, cos inverse of negative 0.5 is equal to 120. Okay, so the angle between them, say we call this phi, is just 180 minus 120 is 60 degrees. And so here now we can go back and input that into our equation. 1 minus 13 cos of 60, and cos of 60 is just equal to 1/2. So 13 times 1/2 is 6.5. So 1 minus 6.5 is negative 5.5. Okay, so that's a geometric way to solve this problem. Okay, so now let's take a look at a more algebraic approach. And I'm going to use the fact that the magnitude of a vector squared is equal to that vector dotted with itself. Okay, so again, I'm still left with 1 minus 13A dot B, Well, what I can do is determine a dot b by using the fact that the magnitude of a plus b is equal to root 3. So that means that the magnitude of a plus b squared is equal to, well, root 3 squared is just 3. So I can now turn this into a dot product. It's just a plus b dotted with itself. All right, and now again, I'm going to use the distributive property. So I have a dot a, which is just the magnitude of a squared. I'll skip writing it out. Here I've got a dot b plus b dot a, commutativity. So that's just going to be plus 2a dot b. And then b dot b is just the magnitude of the vector squared. Sorry, it's getting a little small here. But here, look at that. Magnitude of a squared is 1. Magnitude of b squared is 1 because they're unit vectors. So I have 2a dot b is equal to 3 minus 1 minus 1. Okay, so a dot b is equal to 1/2. And now I can stick this back into my equation, 1 minus 13 times 1/2, and that should look very familiar. It's exactly what we had before. So 1 minus 6.5 is negative 5.5. So, it's tough to say which one is quicker, but just to show you how you do have alternatives in a question like this. All right, so let's recap. First of all, given an expression like this, it makes much more sense to apply the distributive property and write it in terms of simpler expressions. So in this case here, we were able to turn this question into a question of determining a dot b. Okay, the extra information that was given was this magnitude of a plus b equals root 3. So from there, we had two options to solve this. Take a geometric approach by actually calculating the angle between them, or take an algebraic approach and use the fact that the magnitude squared of a vector is just a vector dotted with itself. All right, so a couple of options here to solve this problem. That's it for this one.